Hi guys, welcome back to another video on my channel. It's been a long time, but I wanted to come back with something meaningful. So in this video, I want to do something that's a very interesting topic in theoretical physics. For those of you who are studying theoretical physics, this will prove to be very useful if you were struggling with this concept or idea before. And those of you who are not studying theoretical physics but are aspiring in that direction, this video will show you what theoretical physics at a master's level is really about. With that being said, let's get started. Okay, so today we're going to discuss non-abelian gauge fields. These are fields, and I'm assuming you have encountered fields in a classical field theory or quantum field theory course. So gauge fields are fields that arise when there is a local symmetry. So if we have a regular, let's say, scalar field, phi, with a symmetry uh, that transforms from phi to e to the I, epsilon to mu a sub mu of x phi, such that it keeps the action invariant under such a transformation, then we know that there's indeed a local symmetry that's generated by this a sub mu of x. It depends on x, so that's why it's local symmetry. So this a sub mu is called a gauge field that generates this this gauge symmetry. Now this field in general is a Lie algebra valued one form or a Lie algebra valued field, which is expressed in terms of linear combinations of the Lie algebra bases that we're working in. In this case, we're going to be discussing more general Lie algebras, non-abelian Lie algebras rather than abelian ones. And the action for this gauge field A is given by the trace integral d4x minus 1/4 f sub a mu nu f to the a sub mu nu, where the mu nu are the space-time indices for the Minkowski four-dimensional space we're working in, and the a is a gauge index, which essentially is an index on the Lie algebra we're working in. So that's why we have to trace, because each of these elements are actually matrices. So to get a scalar for the action, we have to take a trace over all of them. Okay, so moving on. F, which is the strength, the field strength of this gauge field, is given by a bunch of partial derivatives of the minus sign with anti-commuting indices, plus g times f sub to the abc, ab sub nu, ac sub nu, where again this a mu is a Lie algebra valued one form, and these f, abc are structural constants which arise from the natural definition of the Lie algebra given by the Lie brackets. So Ta, Tb were the basis elements of the Lie algebra. Their Lie bracket is defined to be I times structure constant ABC T sub C. Now we can always multiply by T, contract by T sub A on both sides of the equation. We get F sub nu nu equals partial nu A sub nu minus partial nu A sub mu minus Ig, and the commutator is A sub mu comma A sub nu, where this commutator term can be seen along with the trace once the trace acts on it to be arising from the Cartan killing form. So for an abelian gauge Lie algebra, abelian Lie algebra, we would not have this term, which makes sense because for abelian Lie algebras, the Cartan killing form is identically 0. Now, the transformation of gauge fields, how do these gauge fields transform? Under, again, the same kind of transformation that we had for the phi. What is their transformation? Well, they transform in a slightly different way. Let's call the transformation generated by alpha as a to the alpha. It's given by the regular a plus 1 over g partial derivative of alpha plus fabc a, capital A, times alpha, where I can just call the rest of this, which, we're ignoring the a, the rest of it can be just written as the covariant derivative. So this is the transformation of a to a under the one parameter family generated by alpha sub a, which is actually a scalar field because it depends on x. Remember, let me remind you, these are all local transformations. So phi sub a is a scalar field, and then if we multiply by t to the a, it would become an element of the Lie algebra. So such transformations, we can check that, preserve S of a, and therefore are a symmetry of the theory. That's the definition of being a symmetry of the theory that's given by S of a. But we care about the correlation functions in quantum field theory, which are nicely defined, whatever that means, via path integrals. And that's given by, again, the trace of exponential of the I times the action of A times whatever field O of A, the operator of the field A that we're trying to calculate in this correlation function, and we take a path integral of that. Divide by the normalization term. So that's trace of path integral over capital A exponential I S of A. But A to the alpha is physically equivalent to A because they give the same theory, their symmetry of the theory, as alpha varies, which is what we mean by a gauge symmetry of the theory. Now, the problem this redundancy or this symmetry poses is that if we look at field space, so this is the space of all possible configurations of field A, each of these circles in field space, where we sort of go around in increasing alpha, represents physically equivalent fields because, well, their a to the alpha is physically equivalent to A. That's why. So this is the best way of representing this equivalence class to these circles, to these gauge orbits, and their redundancy. So if we were taking the path integral over capital A and we go around this alpha direction for each of these circles, we would be overcounting because each of these circles corresponds or represents just one field in the eyes of the theory that we're working with. So we have to restrict that from happening. We have to stop going around the alpha directions. That means we have to fix alpha to alpha naught. And let me remind you, this condition is not just choosing one value for a function. This is a field. So we're just setting alpha of x to alpha naught of x. This is a field. That's what we have to remember. Now, the problem still persists of intersecting each gauge orbit twice. So, because we still don't know what direction of integration. What if we, after fixing alpha to alpha naught, our integration path is such that, we sort of intersect back onto, this gauge orbit, the first gauge orbit, for example, again. Then in our path integral, we would have a redundancy at the point of intersection in the gauge orbit. And we don't want that. We don't want any kind of overcounting. You can take that to violate the definition of the path integral, whatever that may mean, because I know it's not mathematically rigorous enough. but we just don't want any redundancies in our path integral is the point of this. So to combat this issue, we define the Feynman-Tooft-Landau gauge, which is a functional on the field space. So G of A equals partial of A plus W. And we will be setting G of A to equal 0. Now what that does geometrically in this picture on the field space is it's actually a hypersurface. I couldn't draw a hypersurface, that's why I draw a line. Gives us a line G of equals 0. And our integration is going to be along this line. And you see that this line only intersects each gauge orbit once. That's what the purpose of this gauge fixing condition is. So to impose this condition, let's start with this definition. So if we have path integral over alpha, which is a field, so we can do that. Delta alpha minus alpha naught, where we're taking this delta to be a functional delta distribution, which is a delta distribution on the field space. Set that equal to 1. By analogy, this is 1 by analogy to regular delta functions of regular functions. And we're using the property, recall, delta of g of x is delta x minus x naught divided by absolute value g prime of x naught, where g of x naught is 0. So x naught is a root of g. We use that property on this alpha minus alpha naught. So we get delta of alpha minus alpha naught equals delta of g. So we're introducing the capital G, the gauge function now. G of a to the alpha. Determinant, this was the single variable case. This is the multivariable case. And since g is a functional, we have to take the functional derivative. So determinant of the functional derivative of g with respect to alpha, evaluated at alpha naught. Now to make this consistent with our gauge fixing condition, g equals 0, we set alpha naught such that g of a to the alpha evaluated at alpha naught is 0. Because, it had to, the x naught had to be a root of the g. In this case, the g was the capital G of alpha. Perfect. With that in place, we can rewrite our property here of the functional delta in terms of this gauge, delta of this gauge condition. So 1 equals path integral over alpha, delta of g of a to the alpha, determinant of functional derivative of g with respect to alpha. This is, you can call the first Fadeev-Popov trick. Because now if we consider the numerator in that correlation function, trace path integral over a, O of a, exponential I as a. This, according to this first Fadeev-Popov trick, is the trace path integral over a, path integral over alpha, delta g of a to the alpha, determinant of functional derivative g with respect to alpha, O of a, e to the I as a. And let's expand g of a to the alpha. We knew what g of alpha was. Instead of, we knew what g of a was. We now plug in, instead of a to the alpha. So all that does is changes a few terms. So we have partial with respect to a plus 1 over g, partial with respect to the covariant derivative ab alpha b plus w to the a. So when we take the functional derivative with respect to alpha, we get 1 over g partial mu covariant derivative mu ab. Now what we're going to do is we're going to change dA OA SA into dA alpha OA alpha SA alpha, because all of these guys are gauge invariant. The measure, the dA, is gauge invariant because we're path integrating over all possible gauge fields. O of A has to be gauge invariant because we're trying to find a correlation function of that. And for O of A to be an operator of this theory, that it has to respect the gauge symmetry. And S, the action, is naturally gauge invariant because, this gauge transformation is a gauge symmetry. And once we do that, we relabel A to the alpha back to A, because we can relabel our fields. We're integrating over all fields. This is like changing your variable name in a definite integration. So we have trace path integral over A, O of A, e to the I S A. This is just, now nothing depends on alpha anymore. So we can just pull out the path integral over alpha, trace path integral over A, delta, I'm expanding what g of A is. It's the derivative of A plus W, and multiplied by the determinant. We found out what the functional derivative is. We can just put that in. 1 over g, the derivative of the covariant derivative, O of A exponential ISA. Now, this is a little not obvious. Introduce this path integral dw exponential minus I d4x integral w squared over 2c. We can do this because we can just multiply by this term. We can totally multiply by these arbitrary terms because we normalize in the correlation function expression. That, remember, at the end of the day, we're actually dividing. Where's the definition? We're actually dividing by this normalization factor. So whatever we introduce on top, as long as we introduce in the bottom, it will cancel. It will not affect the value of the amplitude that we want to calculate. Because the advantage of doing this is because when we evaluate the functional integral over w of the exponential minus I integral d4x w squared over 2c, along with the delta of this gauge condition, which is the derivative of A plus W, the W changes into exponential I d4x, derivative of A the whole squared over 2c. So the W changes into this derivative of A. And we no longer have this annoying delta to bother us. So the numerator we started with of the correlation function is up to some normalization, which that's why I'm not writing equal. There's this normalization, this integral, path integral over W that we have just introduced. So is up to some normalization. Trace path integral over A determinant of this quantity O of A exponential I SGF of A. Now GF, the gauge field action, is the trace integral d4x minus 1/4 f a mu nu f a mu nu minus 1 over 2c derivative of A squared whole squared. This derivative is coming from the delta, and this f was what we had naturally before. Now how do we work with this determinant? So this is the second Fadeev-Popov trick, is to write the determinant as a path integral over fermionic fields, which I'm going to call C bar and C. So path integral over C bar and C, exponential I d4x integral C A bar minus derivative of the covariant derivative CB. And how is this, why is this the determinant? Well, we can evaluate this path integral by chopping this path integral into a product of the integrals over these individual fields. We're going to chop them in time, which is essentially the definition of this path integral in the most, say, hand-wavy sense. If a product from 1 to n, and again, we take the limit n goes to infinity, but that's sort of not important. Integral dci bar, integral dc, exponential minus ca bar a to the ab cb, which I'm going to set a to something in the end. Now notice that if we expand the exponential that we have 1 minus c bar ac, the summation is implied, and the quadratic term, 1/2 c bar ac, c bar ac, plus higher order terms, which we will show that they go to 0. So we have 1 minus c bar ac minus 1/2 c bar ac bar c ac. What I've done here is I've interchanged the c and c bar, and we get a minus for that because the these fermionic fields are anti-commutating, they're Grassmann variables. So we have 1 minus c bar ac minus 1/2 c bar squared. This a is just a number because it's being summed. A squared, and then same thing. So we can pull both the a's in the middle, a squared, and we have a c squared. Now, since they're Grassmann valued, c bar squared and c squared are identically 0, and we just have same with the higher order terms. So we just have the 0th order term, which is 1, and the linear order, which is c bar ac. So let's choose a nice basis where c bar prime and c prime, where a is diagonal. Advantage of doing that is when we rewrite our exponential over the path integral, we have product from I equals 1 to n, dci bar prime, dci prime. And we have, instead of the exponential, 1 minus c bar prime, a prime, c prime. Since a is diagonal, we can just pull it out. That just becomes a prime jj, where we're actually doing a product over j, which I'm suppressing here. Product from I equals 1 to n. Integral dci bar prime, ci bar prime. Integral dci prime, ci prime. Which, according to the rules of Grassmann integration, just go to 1. And a product over the entries, because it's diagonal, so we're doing a product over all the entries, the diagonal entries, is just the determinant of a, which is invariant of whatever basis we're working in. So that's just the determinant of a. So therefore, for us, a to the ab was just the partial derivative of the covariant derivative to the ab. And we're absorbing the 1 over g into the definition of the c and c bars, which we can totally do. They were kind of arbitrary. We can scale them up and down. The measure is invariant. So finally, putting all these things together, Fadeev-Popov's first trick, Fadeev-Popov's second trick, we get that the numerator of the correlation function is proportional to the trace, the path integral over a, path integral over c prime and c, O of a exponential I s Fadeev-Popov fp of three fields a, c bar, and c. And in the end, what is SFP? It's the trace integral d4x minus 1/4 fa mu nu minus 1 over 2 c partial of a squared plus ca bar prime in brackets minus partial derivative of the covariant derivative ab cb. So the first term was the field strength of the gauge field term, which we started with. This is coming from the delta, from the gauge fixing condition. And this third, which are given by c bar and c, I should mention that they're the c bar and c are Fadeev-Popov ghost fields. That term is coming from the determinant. So essentially, because we introduced the gauge fixing condition, we got a delta of g, which gave us this partial of a squared term. And we had a functional determinant term, which just gave us these ghost fermions. And we call them ghosts because these are not only fermions, but they're also integer spin. Fermions are usually half integer spin. These are fermions with integer spin, and therefore kind of unphysical. They're ghosts. So that's it for this video, guys. Please let me know if you have any questions. I've tried to be as consistent as possible throughout this video because I know that this topic is very tricky and actually mathematically not so well defined, or even if it is well defined, it would leave the domain of physics to actually explain it in detail and go into the territory of pure mathematics, probably at like a higher graduate level, a PhD level probably. And I don't want to really keep that on my YouTube channel for now. But if you have any questions, let me know. I've tried my best. It was difficult to keep track of the different nomenclatures. What is a gauge symmetry? What is a gauge field? Things aren't really well defined in mathematically in theoretical physics, but that's just the name of the game. I hope to actually do more rigorous study on gauge connections. This is actually a gauge connection because this field is defined and then it changes at each point. So to actually take the derivative, one has to introduce or sort of take into account the fact that we're at different points when we take the derivative, and therefore the transformation law is different, which is why we introduce the covariant derivative to transform nicely like the field under such a gauge transformation. But yeah, I think that's really it for this video. Please let me know by email if you have any pertinent, burning questions. Stay tuned for more content, and peace out.